As soon as it starts to spin, the needle will also move along with it. That is, in the direction of the spin, the needle will also move away. So galvanometer is actually designed to interpret or simply measure very low amounts of current. It is just there to detect current. The voltage drop between these two terminals, or simply the voltage between these two, will be equal. The voltage will be same. Only current will be differing. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about moving charges and magnetism in the topic moving charges and magnetism. So let's dive right into it. So for the final portion, we will be discussing about moving coil galvanometer. So what is this moving coil galvanometer? Let's keep the moving coil aside and let's focus on the galvanometer. So what exactly is a galvanometer? So we do know that we use galvanometers in the lab to detect the direction of electric current, or simply we can say that galvanometer is a device which detects small amounts of electric current. That is, it is a highly sensitive device to electric current which can tell you in which direction the current is going. So there will be, if this is the galvanometer, then we can say that this equipment, that is the galvanometer, will tell you in what direction the current is going and if any current is present in the circuit. That is, if you connect this to, let's say, any circuit, then we can say that if there is a current flow through the circuit, the galvanometer needle will deflect to either one of these two sides. Then we can say that yes, there is current flow in the circuit. So galvanometer is used to detect small amounts of current, or generally the current flow in any circuit. So our objective is to find out what is the theory behind this moving coil galvanometer. So we do know that galvanometer detects small amount of electric current, which means it should be a really sensitive device for current. So how exactly are we going to make this moving coil galvanometer? In itself, the name is there. It is a moving coil. So we do know one thing, that is, if any current carrying conductor is placed in a uniform magnetic field, let's say this is the north and this is the south poles, and if we keep a uniform current carrying coil, we remember from the previous derivations. So if we are placing a current carrying loop in between these two magnets, that is inside a uniform magnetic field, so this will experience a torque, and that particular torque will make it to spin. So that particular small principle is being taken here and it is being applied so that we can make a device that can detect electric current. How exactly that is will be explained right now. So imagine that there are two magnets. Let's say this is north and this is south, which means there is a uniform magnetic field from north to south. Now, if I keep a current carrying coil like this, let's say this is a current carrying coil, then automatically we know that it will experience a torque and this will go for a spin. Now, when this particular coil is going for a spin, what if I attach a needle to it? Or basically a pointer. If I attach a pointer to it, as soon as it starts to spin, the needle will also move along with it. That is, in the direction of the spin, the needle will also move away. Which means that as soon as I introduce current into this particular loop, this coil will experience a torque and this will start to rotate. Now, when this coil starts to rotate, this needle will move. That is, the needle will deflect along the direction of the current flow, or simply it will cause a movement in the needle, which we can assume or clearly know that the needle is deflecting because there is current flow in the circuit. Now, that is the basic principle behind this. Since we want to detect the current flow over and over again and not just use it one time, the problem here is that as soon as it gets the current flow, this particular current carrying coil will rotate and the needle will start its deflection, or it will move along with the rotation of the particular current carrying coil. But our problem is that we have to make sure that, so after this particular turn, that is when the current flow is cut off, we have to make sure that this equipment returns to its initial equilibrium position. We can't just say that, okay, current was passed through that circuit, now this needle indicated that current flow, now it is being stuck there. We can't go manually rewind it every time so that the needle goes back to its initial state. So for that, we introduce a little trick in physics. That is how we can restore something after it's being applied once. So what we did was we used a spring. So the simple trick is that if we use a spring, that is, if we use a small spring like this and the needle is connected to the spring, let's say this particular needle is connected to a spring, then we can say that as this coil rotates, that is, in the uniform magnetic field, when current is flowing through that, this particular coil experiences the torque and it rotates. As soon as it starts to rotate, this particular needle will also deflect along the coil's rotation. So when this needle deflects or when this needle moves, along with the coil, what is being wound up? A spring is being wound up. So this particular spring will be wound up. It will gather energy so that when it wounds itself and the current flow is cut off, the spring or initially this particular coil which was turned to a particular direction, the spring is now at a state of stress, which means as soon as current flow is cut off and the torque is released, it will experience a restoring torque. The spring will make it to unbound. So initially this was the state and it experiences a torque, it rotates, the spring winds up. And when the current flow is cut off, the spring is now free to exert its own torque because the current flow is cut off and now it unwinds. So basically the needle will move as soon as the current is cut off, it will come back to its initial state. So basically we achieve that using basic simple physics principle. There are two magnets situated like this and there is a coil. Let's say this particular thing is known as a soft iron core, it doesn't matter. Inside that there is a coil kept like this and inside that particular coil there is a spring. So just like this setup. So inside this particular area a soft iron core is kept encasing the coil and the spring. So inside the particular soft iron coil there is a spring and a pointer connected to that. So because of all this theory, that is the torque, the spin, the unwind, we'll have a moving coil galvanometer. That is how exactly the galvanometer works. And now let's get into the theory. Since these two torques are produced and they are equal in magnitude, we can say that at equilibrium position, that is at equilibrium, tau d, that is this particular torque is the torque that is making the needle deflect. So I'm calling this as torque of deflection. This particular torque of deflection is equal to restoring torque. That is, afterwards, when the current flow is cut off, the needle should return to its initial position. For that, the spring will apply a torque. That particular torque is known as restoring torque. That is denoted by tau r. Now we can say that tau d is equal to tau r. Now we already know what is tau d from the previous derivations and we know that to be NIAB. So if there are n number of turns, then we can say that it is NIAB. This particular torque is written as NIAB. Now we already know that IA is nothing but the magnetic dipole moment. But we are not going to write it as such because we have further use for this particular equation. So I'm just going to write it as NIAB. Know that that is deflection torque or the torque experienced by the current carrying coil when kept in a uniform magnetic field. Now, what is restoring torque? We don't know anything about restoring torque. The only thing we know is that as much torque is applied, that much deflection is produced on the needle. That is, as much torque the spring is exerting on this particular coil or as much torque the spring is exerting, that much turn is being produced, which means that as much torque is experienced, that much deflection in the needle is being produced. So, when the spring is only wound up little, then we can say that the deflection in the needle is also very little. When the spring is wound up even harder, we can say that the deflection is even larger. So we can say the restoring torque experienced will be directly proportional to the deflection. And now we can say that the deflection angle is indicated by the letter phi. So phi is nothing but the angle of deflection, or simply deflection. So we can just directly say that tau of R, that is restoring torque, is directly proportional to the deflection, that is phi. Now, whenever there is a proportionality sign just like that, we have to introduce a constant and make it into an equation. So we can write it as tau is equal to k phi. In this particular equation, we can say that k is nothing but torsion constant. That is, k is torsion constant. You don't have to worry too much about the torsion constant. You don't have to understand or evaluate how that came into place and all that, because it's just a mathematical constant. The thing you have to worry about is that restoring torque is equal to k phi. There k is the torsion constant and phi is the angle of deflection. Now we have two equations. So we can equate them together and we can simply write it as such. Now we have an equation to find out what is the angle of deflection. So we can say that phi is equal to, that is the magnitude of deflection. The magnitude of deflection is equal to NIAB divided by K, or simply the amount of current actually controls how much of deflection is actually being produced, and the sensitivity is also concerned. So the number of turns is also a factor here. A is also a factor, magnetic field is also a factor, but importantly, most importantly, what we are measuring is that the angle of deflection phi is actually concerned with the amount of current. So it actually makes the galvanometer do its thing. That is, if current is flowing through that, it has to detect that and cause a deflection. So this particular relation, you should know that. And one more thing is that since galvanometer is a highly sensitive device, we have to make sure that the current sensitivity of that particular device is up to par. So how can we make it so that it detects very low amount of currents? So we'll discuss that right now, but this particular equation is very important. This equation tells you that deflection is equal to NAB by K all into I, or simply the factors that is affecting the deflection. Okay. Now again, I told you we have to make sure that it detects, that is the moving coil galvanometer, it detects even small amounts of current. So how can you make sure that when current is passing through, that is even small amounts of current is passing through, we have to make sure that it detects and it is sensitive towards that small amount of current passing. For that, we have what is known as a current sensitivity equation. So we have the final equation ready here. The only thing we have to do is that we have to take the I to the left hand side denominator. So we can say that deflections per current passing, or deflections per ampere, will be equal to NBA divided by K. That is, if you want to detect even small amounts of current, the only thing you have to do is that increase the number of turns. That is, N value should be increased so that we can detect even small amounts of electric current. As the number of turns increase, we can increase the sensitivity of a moving coil galvanometer. So this is not just for current sensitivity, but can we do it for voltage sensitivity? Can we increase the voltage sensitivity of a moving coil galvanometer? Sadly, there is a problem to that. That is because the equation says that phi is equal to NAB by K into I. So if we want it in terms of voltage, we have to use Ohm's law, which states that I is equal to V by R, or IR is equal to V. So we can substitute that equation here and we can simply rewrite it as phi is equal to NAB by K into V by R, or simply in order to get voltage sensitivity we can write phi divided by V is equal to NBA or NAB divided by K into 1 by R. So, but both the equations look very similar. Can't we increase the number of turns again to find out voltage sensitivity? Not exactly, because as we increase the number of turns, current sensitivity was increased. But here in this particular case, if we increase the number of turns, the problem is that resistivity also increases along with the number of turns. So as we increase the R, that is the resistivity factor or simply resistance factor, goes incredibly up. So since resistance is also increasing, we cannot simply find out voltage sensitivity by increasing number of turns. So that is one small thing you have to remember. So this is an equation regarding voltage sensitivity and this is regarding current sensitivity. We can increase current sensitivity simply by increasing the number of turns. But we cannot do that for voltage sensitivity because resistance will also increase and that will cause a slight problem. Now, one more important thing is that we can actually convert our moving coil galvanometer into an ammeter. So what exactly is an ammeter? That is one more question we face. So ammeter is a device which can measure current flow. So galvanometer is a device which can detect the presence and direction of a current flow in a particular circuit, but ammeter will give you the actual value, that is how much current is flowing through that particular circuit. So how can you convert this particular galvanometer into an ammeter? That is the question. So let's say my dear friend who's studying in PU comes running to me and he's saying that accidentally I destroyed an ammeter in the lab and I want to make another one. Can you please buy one for me? And me being such a sweet, innocent friend, I'll say that, okay, give me 500 rupees, I'll buy you a new one. Then what I'll do is that I'll take an old galvanometer which is lying around in my lab and simply convert it to an ammeter. And the cost I'll have is like 10 rupees. And I'll save that 490 rupees. So how exactly can I do that? How exactly can I ensure that this particular galvanometer is converted to this ammeter? So the trick behind that is very simple. So the actual working principle behind this particular phenomena is that I have to ensure that the amount of current passing through this particular galvanometer reaches the exact amount of current that is passing through that. So the problem behind that particular method is that, so galvanometer is actually designed to interpret or simply measure very low amounts of current. It is just there to detect current flow. So what I'm trying to do is that I'm trying to measure huge amounts of current using this particular galvanometer, which means if this particular galvanometer reads 10 microamperes or something, then I have to make sure that if 10 amperes of current is passing through that or 10 milliamperes of current is passing through that, I have to make sure that the galvanometer still reads 10 microamperes or simply reads 10. The needle points towards 10. That is the only thing I have to make sure. So even if a higher amount of current is passing through, the needle should point towards the magnitude of that. So how can I actually make sure of that happens? So that is where we use a little trick. So we know that current travels or chooses the path which is having least resistance. So if you have two roads and one is very bump filled and has a lot of gutter, you will try to instantly avoid that, right? Just like that, current will also try to avoid any road which is having a higher amount of resistance. So what we are going to do is that introduce a higher amount of resistance to the galvanometer and the least resistance path just parallel to that, so that the current splits up in such a manner that the galvanometer will still read the current to be the magnitude value of the entire current. That is, using a simple physics trick, you don't have to complicate your mind about that. Simple thing you have to know is that the current, that is, let's say I amount of current is passing through this particular circuit. Then when it reaches the junction, it splits up into two currents. According to Kirchhoff's rules, we have to know that the current splits up. So Ig amount of current passes through the galvanometer and I minus Ig amount of current passes through the resistance. I haven't clearly disclosed how much the resistance is. I'll tell you that. But yeah, I minus Ig amount of current is passing through here and they rejoin at the other junction and exit through as I. Now, why did I just do that? The reason why I did that is because I knew if I split the current, I can make sure that the galvanometer points to a reading I actually want. That is the magnitude of the current. Because the voltage drop between these two terminals, or simply the voltage between these two, will be equal. The voltage will be same. Only current will be differing. The voltage across these two terminals will be same, but the current will be different. So that is why I am choosing this particular setup. Using this particular setup, I can ensure that this galvanometer reads the amount of current I want. If that is all confusing, just know this. If there is a galvanometer and we want to convert it into an ammeter, simply connect a resistance in parallel. Always make sure in parallel. A resistance in parallel to the galvanometer connected will make it into an ammeter. One more condition is that the resistance should be a very low one. That is, if the galvanometer is having 100 ohms of resistance, that is, if the galvanometer resistance is 100 ohms, then this resistance we are connecting parallelly should be very small in the magnitude of, let's say, 1 ohms or like 0.1 ohms or 0.10 ohms, like that. It should be very small. So this is a very small resistance that is connecting. Now, why did I just do that? The reason why is because I want to ensure that most of the current flows through this particular circuit, so that the current flowing through this will be comparatively low, but it still reads the value I want it to show. That is, if 10 amperes of current is coming through like this, the current will split in such a way that even though the galvanometer can only read up to 10 microamperes or 10 nanoamperes, it will be going in such a way that the needle will still point towards 10. The needle will still point towards 10. So I'll still get the value and nothing is being disrupted. The only thing I added was I added a parallel resistance to the galvanometer just to make sure that most of the current flows through this small resistance. And the resistance connected is very small because I want most of the current to flow through that only. So this small resistance is actually called as shunt resistance. And this shunt resistance should be very small. The reason why it is very small is because if two resistances are connected in parallel with each other, then the effective resistance will always be less than the least resistance. That is, one thing you have to remember about series and parallel connection, always remember that if two resistances are connected in parallel with each other, here it is galvanometer resistance 100 ohms, here it is small resistance or shunt resistance which is 1 ohm, then the effective resistance of this particular circuit will always be less than 1. That is, less than the least resistance in the circuit. So when resistance are connected in parallel, then the effective resistance will be less than the least resistance. If you want to do it, we can do it. 1 by R is equal to 1 by 100 plus 1 by 1. So simply it is 101 divided by 100, or simply it is equal to 1.01. Now this quantity is 1 by R. We have to find what is R. So effective resistance R will be equal to 1 by 1.01, which is approximately equal to 0.99 some digit. So so it will be 0.99 something. Effectively, it is less than the least resistance. You can try it out. So now we have created our ammeter. So this is the process of creating an ammeter out of a galvanometer. So in order to convert a moving coil galvanometer into an ammeter, it is very simple. You have to connect the galvanometer to a small resistance which is parallel in nature, and the small resistance should be very low in value. That is, if we have 100 ohms of resistance, it is better to have 0.1 or 1 ohms of small resistance, comparatively very less. That will ensure the current flow is maintained mostly through that particular circuit. So now we know that the voltage drop across the both terminals will be same, and we have predicted this will act as an ammeter. The equation regarding the conversion of a moving coil galvanometer into an ammeter, since the voltage drop across the terminals will be same, that is, the voltage here will be same as the voltage here, we can equate those together, and simply by using Ohm's law we can write, we know that V is equal to IR, and here simply voltage will be same, which means I into R will be same for both. So we can say that I here is nothing but I minus Ig coming through here, and R here is nothing but the small resistance or shunt resistance. So we can just say that Ig, that is current passing through the galvanometer, into the galvanometer resistance will be equal to I minus Ig into S. Now we can understand that how we can get the formula in order to build an ammeter using a moving coil galvanometer. So simply we can find out what is the small amount of resistance needed if we know what is the current passing through and the galvanometer resistance. Or if we know the resistances, we can find out what are the current flowing through that particular circuit. So anyways, this is also applicable in your lab, that is, you will be doing this particular experiment and finding out the values. So we'll talk more about it during the lab time. Last but not least, we can also convert the moving coil galvanometer into a voltmeter. Here we have to increase the resistance, that is, we have to produce a large amount of voltage drop. So simply, if you don't remember, voltage tries to push across the electrons after any hurdle. That is, if this is a circuit, let's say this is the circuit, and if there is any sort of resistance here, then this particular battery will try to produce more voltage so that they can push over that hurdle. That is, the electrons can push or jump over that particular difficult situation, in this particular case resistance. So in order to have a higher voltage drop, that is, to make it more voltage sensitive, to convert it to a voltmeter, we have to introduce a high amount of voltage there. That is, if this is the circuit and this is the galvanometer connected, then in series with it we have to connect a high amount of resistance. That is, if this particular resistance is high, then we can convert this whole equipment into a voltmeter. So this will detect voltage across those two terminals, or what will be the voltage passing through that particular equipment. Here now this is converted into a voltmeter. Here the current will be same, the only thing is that the voltage will be differing. So as you increase R, that is, R should be a really high value. If you increase R in the terms of millions also, it is completely fine. That much voltage it can detect. That is, that will be a good voltmeter if R is of a high value. So we can say that from Ohm's law again, that is, V or I is equal to V by R. Simply we know that in order to find out voltage, that is, V is equal to IR again, or simply we can write that since resistance here is the sum of galvanometer and resistance connected, that is, there are two resistance in the circuit, one is galvanometer resistance G and one is the resistance we connected in series, that is R. Since they are connected in series, we can directly add them together and we can say that this will be the effective resistance of that particular circuit, or simply we can say that V will be equal to the current passing through, let's say it's I into G plus R. So this will give you your equation for the voltmeter conversion. If you want to convert a moving coil galvanometer into a voltmeter, you can use this particular equation. And it is very simple. So if it is connected in series, we make a voltmeter, and if it is connected in parallel, we make an ammeter. So that is the only thing you have to remember about this and the equations pertaining that. So I hope you have understood about voltmeter conversion, ammeter conversion, and the theory behind moving coil galvanometer. I hope there is no doubt. So we'll discuss more about conversion of moving coil galvanometer into an ammeter and voltmeter in the lab sessions. So until then, I'll see you all and I'll be back with a new chapter. Thank you.